Hello everyone, I'm excited to be here and share an amazing story with you. I used to teach at the University of California, Berkeley, and I thought the beginnings of this story was so amazing that I quit. And instead I joined a startup called Enlytic, which is taking the state of the art of a technology called deep learning and applying it to medicine. Before I talk about Enlytic and data-driven medicine, I want to take a step back and talk to you about the underlying technology, deep learning, because it's really amazing and it's starting to appear all around us. And I think we're potentially at the beginning of an exponential curve of it impacting our lives every day in very profound ways. But at the same time, many of us aren't even really aware that it's happening. So what is deep learning? Deep learning is a way of using computers, so writing code, algorithms, that's conceptually based on how the human brain works. That's a fundamentally new way of using computers. And it's allowing some things that were science fiction a few years ago, or maybe even a few months ago, to actually happen for real. So for example, a couple of years ago, Google had this April Fool's joke for Gmail on autopilot. It would automatically send your emails for you. A few weeks ago, Google actually came out with a real auto-reply feature that will help you automatically create replies that are conceptually relevant to emails that you receive. So 2009's April Fool's joke is today's reality. Another example, Skype Translate. This allows you to translate from English to Mandarin, if you didn't take Chinese, or to German, to Spanish, in real time, automatically, while you're on the call. A third example of a similar technology we heard about earlier today, IBM Watson, training a computer to win at Jeopardy, so basically being able to parse complex sentences in real, regular English language. And as a final example, deep learning algorithms being used to identify people for Google driverless cars, so they don't hit pedestrians, which is obviously pretty important. So what's happening? Why are all of these technologies all of a sudden starting to appear? It used to be that when engineers wanted to write a computer program that could do some of the kinds of things I showed in the previous slides, they would have to find domain experts that sort of translate the expertise of those domain experts into hardwired, hard-written code. So line by line of hard-written rules of how the computer program should behave. So that meant that the computer program could only be as good as this set of rules, only as complex, only as comprehensive, only as robust, and could generally only handle a very specific problem. And very rarely would the computer program be as good as a human being. It wouldn't match what those initial experts could do, because they would only capture a fraction of their insights. Now there's a new way, deep learning. So how deep learning works, it's an artificial neural network, so basically a system of algorithms that on their own can look at data sets and figure out what information within that data set is important for mastering a task at hand. So now all of a sudden, the program can do things that the supervisors, the coders, aren't even explicitly aware of. And the approach can be generalizable. It's not just for a very specific situation, but it can be transferred to do a large number of tasks. That might sound a little abstract, so let me give you a specific example. And this is a visual example of identifying objects in images. And I'll use everyone's favorite examples, identifying internet cats. So let's say you want to build a deep learning network to identify cats. What you would do is create a system of artificial neurons, that is individual nodes of code, but you wouldn't just do one, you would create hundreds of millions of these, and they would be interconnected by different weights, so mathematical connections, to create a huge, large system that's layered. So now you can take complex problems like identifying vastly different images, and you can turn it into lots and lots of smaller problems, so hundreds of millions or even billions of tiny mathematical problems instead of one big initial problem. The next key thing is to iteratively try to solve your problem, like identifying the cats. You show this network an image archive, let's say, of thousands or millions of images, some of which have cats in there that are labeled. You then test your system, letting it look at a new data set and say, hey, find the cats. It might not do so great in the beginning, but it iteratively does this again and again and again and gets better slowly but surely, or actually quickly and surely, until it can identify objects within the images. So we've gone from a system that's really code heavy, engineers writing lots of code, to a solution that's data heavy, so using big data archives to solve complex problems. This has been a long time as a concept, maybe half a century, but it's only within the last few years that the hardware for computers and our human insights about how to write these algorithms, that's been around to make it possible to really use deep learning, not just for a few applications, but really at scale to do lots of different things. So this is pretty amazing. Since 2012, deep learning pretty much blows any other computer method out of the water, for example, recognizing images. And today, it's better than humans at a lot of different tasks, including, speaking of the last presentation, recognizing handwritten Chinese characters. So what does this mean for Analytic and the company I work for? Jeremy Howard, the founder, is a data scientist who basically realized that medical decision-making is a massive data problem that can be tackled by deep learning. And not only is it a massive problem, it's a profoundly important problem because it's about human health and saving human lives. So let's think about really quick how big this data problem is. The World Health Organization recognizes some 12,000 different diseases. Each one of these has a number of possible symptoms, a number of possible treatments. It's really big. At the same time, a radiologist doctor in the US might look at medical images from many dozens of patients within a single day. So it becomes a big problem, and it's perhaps not surprising that a lot of mistakes are made. What Analytic does, it builds algorithms, bigger and more complicated, but based on the same idea as the internet cat. But here, what we're doing is training on medical archives, so past medical outcomes, and the purpose now is to help doctors better and quicker diagnose disease. Concrete example. The arrow here shows a tiny hairline fracture. It makes up less than 0.01% of this image. An analytics algorithm can find it within a fraction of a second, and it can do it better than any other computer that we've compared it with. And maybe more importantly, it can do it better than doctors. The red circle you see around it is a heat map. It's a way for the algorithm to show the doctor it's working with why it thinks there's a fracture there, identify the area. And that's really important, I think, because it means that the technology is not a black box. Instead, it's kind of a collaborative service, let's say, that augments the doctor. So the doctor is always in charge and knows why a decision was made or why a recommendation was made. A second example, lung cancer. It's one of the most common and most deadly cancers in the United States. Analytic's deep learning algorithm can perform better than a panel of 4 human expert radiologists. We've done this against publicly available benchmarking tests. And not only is it better, it's 50% more accurate, a huge improvement. And not only can it tell that there is a cancer marker within that person's lung, it can also predict the malignancy. So the chances this is a dangerous cancer rather than a benign formation within the lung. And then thirdly, and I think maybe most interesting, it can also get us closer to personalized medicine. It can bring out examples of prior patients similar to the patients right then and there and show the doctor what worked and what didn't work for those prior patients. So those are 2 examples. So X-rays for wrists and CT scans for lung cancer. But I also told you that deep learning is not just about, it's about scalability and also about generalizability. So what we're doing is building a deep learning system for the entire human body and for all of its afflictions. And we're doing this in collaboration with Capital Health right now. That's the fastest growing radiology company in Australia, augmenting their doctors across 52 clinics so that they can work together with deep learning algorithms to better diagnose disease. So 3 take-homes for me. One is deep learning is this new exciting technology that you're going to you're going to be seeing in all kinds of different arenas, not just medicine, but all over. 2, Analytic is using deep learning for a particularly profound problem, I think, human health and medical diagnosis. And 3, we're seeing this not just as a solution here, but as a way to democratize access to healthcare. So one of the first places we're going outside of Australia is to underserved communities in Asia. Thank you.